I'm going to talk about conservation of total mechanical energy. And mechanical energy, by that I mean kinetic plus potential. Remember, kinetic is a real energy, how fast something's going with the mass, combined with the mass. Potential is a placeholder that replaces the work done by gravity. So, when we talk about that, we're talking about a system that involves an object and the Earth, right? You can't have potential energy from the Earth's gravitational field without the Earth. So I will talk an awful lot about the potential energy of the Earth object system. So this is all it means. The total mechanical energy before equals the total mechanical energy of the system after. If there's no work done on the system by an external force, remember I always think of energy as this cloud, this stuff, this characteristic of a system. And if I do work on it by using an external force and moving something, I'm going to increase that energy. If work is done opposite the direction of motion, it decreases the energy. Negative work is done. But if there's no external work done on the system, and again, we're not worried about gravitational work now because that's captured in here, then it's this very simple relationship. What I would strongly recommend is every time you're doing a problem in which energy, you're using the concept of energy conservation, write it down. There is a way to write it, including work, which is like this. External work equals change in the total mechanical energy. That's supposed to be a T there. Okay, can't write all of a sudden. There we go. Work done on the system changes that total energy. But if we're talking about, okay, we're pretty sure there's no external work done by the system, then these two things would be the same. What could change these? Friction could change these. Somebody, coming along and shoving it could change these. But for a lot of problems, you end up having conservation of mechanical energy. I write it like this. I write that first, then I write K plus U equals K plus U both prime. K after some event, after some time passes. So the total energy before equals the total energy after. So, hey, look at this. 1/2 mv squared equals, plus mgh equals 1/2 mv squared plus, and that's v prime squared, plus mgh prime. The mass isn't changing. Hey, but look at that. The masses will all cancel out. That's one of the really nice things. For potential energy, when we're talking about no external forces doing work on the system, doesn't mean no external forces, just not doing work, then the mass doesn't matter. Let me prove that to you. Let me show you what that means. I'll drop a ball, okay? And I'm going to be a little bloody-minded on this one because I want to make sure that the wrong lessons aren't learned. The mass of the ball doesn't matter, but let's say it's 2 kilograms, okay? And I drop it from, let's say, I don't know, here's a table, okay? And I'm going to say that the table is 1 meter high, and I drop it from 0.8 meters above the table. Why am I being this fussy about this? Because I don't want 0 to be the ground. In a lot of problems, you'll want 0 to be the ground, but if I did that right now, it would teach you some bad habits. So, I'm going to call 0 right here. In fact, I need another color because I need to call. This is my 0. This is my reference. That is my height equals 0. My potential energy is equal to 0 at that spot. Okay, that's my reference point. I need that because I need to know what I'm measuring H against. Okay, so what I would do in these problems is I would write right next to the different locations, because remember, potential energy depends on location, and it's going to be traveling different velocities at different locations. So I'd write right next to there all the stuff I know about that. So let's do this. Up here, the potential energy is going to be 2 times 10, 20 times 0.8, which ends up being 16 joules. I'm just doing MGH. And I'm going to release it from rest, just because I'm going to take it easy on me. So the kinetic energy at the beginning is 0. And I want to find out how fast it's going at the bottom, V at the bottom. Well, up at the top, I know the total mechanical energy is 16 joules. I basically just did this, kinetic 0, 16. So I know the total energy at that first mark is 16 joules. Well, guess what? There is no work done on the system by an external force. We're ignoring air resistance. Nobody's smacking that ball down. Nobody's smacking the ball up. So nobody's adding energy to the system or taking energy out of the system. It's all part of the Earth object system. So when it gets down here at the bottom, the potential energy, oh, wait a minute, the height is -1, right? Because I called this 0. So the potential energy will be 2 times 10 times -1 is -20 joules. But I know energy is conserved. It's the conservation of mechanical energy. Therefore, the kinetic energy I can find using this. Total energy. I'll call these prime down there. Okay? The total energy here is going to be 16 joules. Has to be the same. No energy has entered or left the system. 16 minus -20 means this is 36 joules. Kinetic energy is 36 joules. I can then use 1/2 mv squared to solve for that. So really all I did was, instead of using an equation, I put these things where they were and realized that these are equal. The total before and the total after. In fact, anywhere on that trip down, it would be exactly the same. So you'll notice the m's did matter in finding those, but when I find the velocity, and I'm not going to do it right now, you can find it. I'll leave that as an exercise for the viewer. If you take this 1/2 mv squared, 1/2 m is 1, square root of 36, that ends up being really 6 meters per second. That's amazing how, at any rate, no matter what mass you used, if I used a bigger mass, these would be bigger energies, but then when you take out the 1/2 m from K, from the kinetic energy, it'll end up canceling out. So there are going to be a lot of problems in conservation of energy where the masses just don't even matter. If they don't give you the mass, put in 1. Make it easy on yourself. But all I did was this thing like that. Now, I want to make sure I've got some time on this. There are other problems that look like this. Ball on a ramp, or I shouldn't say ball on a ramp, object on a ramp, okay? Block on a ramp. And let's ignore friction. If there's no friction, then the total potential energy there plus the total kinetic energy there, I should say potential plus kinetic gives me a total, and that's going to be the same everywhere. So if I knew what the height was here, I could find the potential energy here. I check that off. I know the total energy because once I find it anywhere, I can find it everywhere else. So I can use that to find out the kinetic energy and then how fast it's going. Or here, right down here, if he told me how fast it's going at this spot, I know the kinetic, and I always know the total because I found it at one spot. So I can use that to solve the potential and find what the height is. So this nice concept, again, total before equals total after, and break it down. Kinetic plus potential equals new kinetic plus new potential. And you can do this at an infinite number of locations. If you know at one spot, if you know what the kinetic and potential energies are, then you can solve for the other spots just by knowing the height. You can find the velocity from knowing the velocity. You can find the height. That's the beautiful part of again, checking the time. That's the beautiful part of conservation of mechanical energy. Now, in the next video, I will do another problem. A roller coaster is a real typical one. By the way, before I go on, look at this. If no external work done on a system, there's an external force. There's a normal force on the system. But remember, as this goes in this direction, that's perpendicular to the delta x. There's no work done by the normal force. That ends up being fairly typical. In the next video, what I'm going to do is I'm going to show you that forgot where I was going. Oh, what happens if you do have work that does change the total energy of a system?